Hello physical science students, welcome to the next video. 10.2 electric currents and circuits, which is part of our electrical energy course. So we've just moved on from static electricity. I only need to know a tiny little bit about that, and so we're now going to learn about electric currents and circuits. And so when a charge flows through an electrical conductor, it usually flows because there is a reason for it to flow, and the reason that the current flows is a thing called voltage, or sometimes referred to as potential difference. So we can use those terms interchangeable. We might say there's a potential difference or there's a voltage applied across the conductor. And so what we end up having is a current. Now that current, most commonly, most of the time we're thinking about current in copper wires, but we could just as equally have a current where electricity is flowing through a solution that has ions, for example. We don't refer to that commonly, but most of the time we're talking about currents in metals, basically. And when we talk about circuits, it's when we've got some design to where those currents go. And so the flow of charge is the electrical current. Alright, and so here in this series you'll find there's a bit of writing on the screen, so it's just a matter of you might want to pause it. I'll talk about it, but you want to make sure you read it as well. And so we know that metals, and mostly metals, but there are other objects that are good conductors. For example, water with ions in it is a good conductor. They have electrons. The metals have free electrons, the delocalized electrons. They're free to move. And then, so when a cell, and that's another term that we're going to introduce, a cell is an old term that people used to use for batteries, because the very first batteries were actually great big bathtubs full of chemicals with various metal plates put them, and they were referred to as cells because that's more a chemistry term. And so now batteries are still referred to as cell, like you have a cell phone. It's not called a battery phone, and that's what with the terminology we're using. And so when a battery is attached to metal wire, the electrons, which are negatively charged, just reminding you, they move towards the positive terminal, and therefore a current flows, and current is those electrons flowing through the conductor. And so in a metal you have, going back to our metallic bonding model, we have the cations, and then you have your delocalized electrons, and they are free to move. So if we put a potential difference or a voltage across there, we get a flow of electrons. Doesn't mean there's gaps of electrons where there's no more, because the electrons have to come from somewhere else to fill in those gaps. And the cell, what the cell or the battery does is it gives the electrons energy, and therefore they move. It pushes them basically, and this push is what we call the voltage or the potential difference, PD. And so that's the representation of a battery in a circuit. The long end is the positive end and the short end is the negative end. That's just the convention. And so here we have a conductor, okay, and electrons flow from the negative end through to the positive end. That's the direction that the electrons flow. Now I need to just go back though, and how no, I won't mention that, we'll mention it later on. So there's different types of circuits, how we can conduct or connect things together. And in a series circuit there's two types of circuits, series and parallel. In the series circuit there's only one path for the electrons to go through. And so if we draw a circuit like this, we haven't touched on the symbols yet, we're going to talk about them shortly, but I'll just introduce you to those. This is our battery, this would represent a light globe, and this is a switch, which you can see is open. Now whilst the switch is open, there's no current flowing. When that switch closes, current will flow. And the confusing thing I was about to tell you is the electrons flow that way. So, and we know that electrons are what's actually moving. But when we talk about what's something called conventional current, okay, which is given the symbol I, what we say for that is that it flows from positive to negative. And if this is the positive end and that's the negative end, we're actually saying that the current flows this way, the conventional current. Now the conventional current is an imaginary current. It relates back to the history of electricity when people were working on circuits and they needed to, because they had invented things that controlled the direction of current, they needed to actually assign a direction for current, but they didn't know about electrons at the time, and so they took a guess. It was a 50-50 guess. Is it positive things carrying the charge or negative things carrying the charge? And they got it wrong. But because so many conventions had been governed by this early work, we still use conventional current as positive through to negative. We just need to know that electrons are moving the other way in reality. Okay, so let's just get rid of that. That's what I was mentioning before. So we close the circuit and the current flows, conventional current, and the light globe works. And this is a little bit just saying that, explaining conventional current too. Now if we open that switch, all the electrons would stop. They don't disappear, they're still there, they're buzzing around their cations, but they have a random path. When current flows, all the delocalized electrons have a certain direction that they flow in. Now a series circuit, like I said before, the electrons only have one choice. And so here, this is a number of cells joined together. So a number of batteries joined together. We treat it just the same as one. The current comes out, goes through this light globe, goes through the switch whilst the switch is open, goes through this light globe, this light globe, this light globe. Now, if the switch is open, none of these light globes would be working because the current just stops. Okay, now you notice that we use this a measure of current, and the measure of current is amps. Now here we've got 0.5 amps, and because it's a series circuit, 0.5 amps is going through every part of the circuit. There's no choice. Now amps is a measure of how many electrons, and electrons carry coulombs of charges. Throwing out a few terms here, we'll get to use them a bit more later on. And so the number of amps is dependent on how many charges, and because charges are measured in coulombs, it depends on how many electrons are flowing. And 1 amp means 1 coulomb of charge in 1 second. So 1 amp equals 1 coulomb of charge per second. Now each electron has a small amount of charge, and so it takes a lot of electrons to carry 1 amp. Now in a parallel circuit, there's branches. The electrons travelling around the circuit have a choice which way they go. And so this is a more complicated diagram. We've still got our battery, we've got switches everywhere, and we're sending 1 amp. The battery is sending down 1 amp of current, and when it comes here, it must split up. And it splits up depending on the load. And the load is a measure of resistance. Electrical resistance. Now of course we've got bulbs here. This branch 1 and branch 2 only have 1 bulb each, and so they get the same amount of current. Branch 3 has 2 bulbs and it gets less current because it's got more load or more resistance. And so you can see that these amps all must add up to the amps that went in, and when it joins up it goes back to being the amps, because remember this is all electrons, and so a certain number of electrons are travelling here. Those electrons split up and then rejoin here, and none are lost. Basically energy can be lost, but the electrons aren't lost. Now if I open this switch here, it means the electrons only have 2 choices to go through, and so the current would vary again, but it would still add up to 1 amp. So that's a parallel circuit, as distinct from a series circuit. Now some of the symbols that we might use: wires joined together. A fixed resistor can be a square or a squiggly line. A variable resistor is one that we can change, so it has an arrow through it. A rheostat is like a big coil which you can slide along and it changes the resistance. That's a lamp, that's a filament globe, which we're getting less and less of nowadays. An earth, we don't use the symbol for. There's a cell, there's a battery of cells, which is, that could be a battery, and that's a series of batteries. A couple of things crossed off that we don't need to know. Most importantly, an ammeter is a circle with an A in it. A voltmeter is a circle with a V in it. Now we don't know what they are yet, but I'll explain them shortly. A fuse can look like that, a switch, and an AC current supply. So you'll see most of these symbols, pretty standard ones, and you get used to them pretty quickly. So in the next video, we're going to actually look at the charge in electric currents. Cheerio!